Are you able to see the screen?
Yes.
All right. Well, good afternoon. My name is Carlos Munoz, and this is.
I'm Dario.
I'm Mitchell.
I'm Ela.
I'm Ali. I'm Aziz.
I'm Ajay.
My name is Luca.
And this is NJIT's RockSat Arrows project, STR review. So we're going to start off with the STR action items. We have updated our user guide compliance and pointed out the high voltage for Langmuir probe. So on page 24. And for the FUR forms, we are still working in progress, which is one of the questions we will talk about after our presentation. Mission statement. The Arrow mission, our NJIT mission is to design and demonstrate a dual-stage sub-orbital platform, Arrow, which utilizes a stationary payload Overwatch as a central hub to deploy Scout. Together, these systems will characterize the ionosphere by measuring electron density and analyzing dynamic forces experienced during reentry. So these are from the CDR, so we are going to skip all mission objectives. All right.
And so we have some updates on software development, obviously. So we were working on maintaining the precise internal clock for the mission, but now that you're saying there's a few changes in it, so we're going to go over the internal clock again and fix some stuff with that. We are going to be obviously developing the control logic for Scout using the stepper motor. So we're working on the gear ratios for a while to understand how much we have to do the stepper motor with the block of code to launch it proficiently on time with efficiency, mechanical safety, obviously, and control release. Obviously, we're implementing C++. I'm repeating from the old presentations. So we have the fastest speeds and data logic and post-mission intelligence. So we have designed a structured logging system to capture the data, obviously. We're going to have a post-mission log system that we're going to use after the mission to do some AI analysis to understand patterns, anomalies, and most frequent sites.
The timer event matrix is different. We have GSE2 at T minus 45 seconds. This will power on Overwatch and Scout. And then timer event 2 at T plus 160 for a 10-second dwell, and it will activate the ejection mechanism. But it's subject to change still. Concept of operations are mostly the same. Still T plus 165 seconds. Overwatch starts logging on. 5 seconds for that. T plus 160. Scout is ejected, and then final data dump is at plus 320. This is unchanged from CDR, just our expected results. This is an example from RockOn, Langmuir probe data. Then we have the IMU. Comprehensive success is also unchanged from CDR, as well as the minimum. Top level requirements unchanged from CDR, and Scout top level requirements are also unchanged.
As a subsystem overview, we do have the entire layout for both Overwatch and Scout with updated components. This is just a closer look of the Scout subsystem review. We have our battery that is powered by our regulators and distributing power to necessary components, and the data lines that are receiving and transmitting data across the PCB boards that we will be using. Next slide. And this is Overwatch's system overview. We still have, this is unchanged from our previous CDR, but yeah, upgraded. Let's continue.
All right, and then we go on to design specifications. This is specifically the weight budget. For the most part, it hasn't changed. It actually got a little bit lower, so we're doing a little bit better there. All the changes that could possibly be made going on now are going to go lower weight as we're removing weight from places that don't need it. As we go through testing, we find that the thickness of this does not have to be 0.3 inches. It can be 1/4 inch or maybe even less. Then we move on to the power weight budget. This does not change from the CDR. This stays the same. Total watt is 6.9 watts. And then for design specification, this is the pin assignments you gave us. We understand we plan to use
TE2 and
GSE2, and then our ground controls. And then for the user guide compliance, we're still in a 1 by 1 inch plate for center of gravity. We're still on our weight budget. Our max height is still below 1.5 5.13 inches. We're out of the keep out zone. We're in the keep out zone, but you guys allow that to happen. And then we updated the more important thing was the high voltage, the 5200 volts for the Lamer probe. And then for RF, we updated that as well to include the rock block. We only had the XP module in there. Now we have the rock block.
Special requests, same as last time, integration of Big Red Sat 1. That's why we're in that keep out zone. And we're still figure out more ways that we can integrate them. Updated descope plan. For the Scout module, we redesigned the tail to optimize use of space. We're going to remove the antenna from the back because it could affect the Lamer probe reading. Scout is thinner now, so we have saved weight there. And now that the back is larger, we have made a larger electronics cage. For the Overwatch module, we changed the unlocking mechanism to feature a worm gear to eliminate the possibility of backdrive. We're using a 3D printed PA612 bracket with sheet metal reinforcements to hold on the stepper motor. We're using a stepper motor with an encoder to mitigate risks of jams. And we are possibly adding a guidance system to just make sure that Scout leaves the capsule without interfering with any other.
Oh, sorry. All right, and then this is the start of the subsystem test review. We split up two subsystems of Scout and Overwatch. These are just overall CAD models of the whole experiment, and then here we have each one of the lines pointing to the whole bill of material. As for Overwatch, the overall power we're using on that is 5,300 milliwatts. The data that we're using is to be determined yet, but we don't think it to be an issue with collecting data that we need to. Overall volume is 87 inches cubed, and the weight of Overwatch, not including, I don't think it's including Nebraska's or the Scout module, is 10 pounds. This whole system will be mounted to the deck using flush countersunk bolts, and we'll be securing those bolts with nylon locking nuts. We'll be connected to wall-ups using the mil-spec connectors coming out of this box, and it's going to go into those connectors that you will provide us. Pins are shown on previous slides. We have not ordered the connectors yet, as we're still wondering how many pins we actually need to come out of this box. Overall size and dimensions have not changed since the CDR. There's been internal changes with just some geometries, but like overall height, 5.08 inches, that has not changed. And then changes that need to be made is addition of another bearing to support the shaft on this edge here. We need to optimize the stepper motor mount just to make it stronger. And then we need to create guides to deploy Scout so it comes out straight and does not go side to side or possibly bend the bracket wall during launch.
As for the Overwatch quick status, we have completed FEA analysis on the cam body structural integrity. We completed a motor mount structural integrity as well, and completed a SolidWorks FEA analysis on random vibration test. We also did some electronic simulation test, which includes system startups, motor deployment, and as for the software, we did a simulation and verification of the entire process. So currently we're at 50% in terms of Overwatch completed test. Our second half would be after manufacturing and testing, everything pretty much together working cohesively.
Okay, and so for the FEA case analysis for the cam body, if you look on the left-hand side of your screen, the one picture that has more of the colors, we put a fixed command on the back because we would be supporting most of the pressure there. And from the stress analysis, we can see that the only really major point of contention or key areas would be the upper portion of that ring, but it's negligible because it should be reinforced. And the strain analysis also shows that everything should be relatively fine there. On the right-hand side of the screen, you'll see the materials we used. We decided to go for a fine mesh instead of a coarse mesh because with the finer the mesh you get, the more precise numbers you'll get as well. And so from the charts, you can see that the FEA analysis should be fine for the cam body. For the stepper motor mount, we did two tests. We did a point load going directly from the top, and we also did a torsional load to calculate or see where the interference would be on the stepper motor mount or the stepper motor mount. And as you can see from on the left-hand side, we'll start with the torque analysis. Everything's fine from there. It's getting most of that impact on the left-hand side, so the right-hand side should be fine. And then if you look on the right-hand side, sorry. If you look at the right-hand side to see the actual point load, the major points of contention would be those side areas, but because the motor will be under it and that'll be supported by the base plate, all that should be fine. So there should be no deflection.
So moving on to vibration results, we're trying our best to replicate what's going to happen at Walt's facility as per the RockSat user guide. So the random vibration test and the sign test. So starting with the random vibration test, we did it at the first location was full thrust, so pointing upwards at 0.051 G squared hertz. And the frequency band was from 20 to 2000 hertz. The picture that you see here is at 2000 hertz. And areas that we stood out to us was in the little corner, if you could see it, it's a small roller for the cam. And looking at the Von stresses, we see that it's 1000 PSI. We did a 3 sigma on that, and the 3 sigma stress, just so we could see how if we increase the stress and compared it to our yield stress, we could see how much of a difference it is. And that was 3000 PSI. And then we look at the yield stress at 61 T6, which is 39 KSI or 40,000 PSI. So that's nothing to worry about, but it's just a food for thought to keep in one in the manufacturing process. The next one is, you can go to the next one, please. The next one will be at the lateral at 0.029 G squared hertz. Frequency is still the same. Again, some areas of concern or areas of thought that we wanted just to look into more is the L bracket from the back of Overwatch. As you can see, that bluish region. Again, it was at 700 PSI with 3 sigmas, 2,139 PSI compared to that yield stress. It's still not an issue, but it's still a good idea to maybe put some supports in the back. I was telling Dario about this, that we should probably maybe weld another bracket in the back. Moving on to the next slide. We have 90 degrees from the lateral, and the frequency is still the same. Once again, the stress was the same as the last test. Nothing to worry about, like I said, but having that extra bracket wouldn't hurt us. Moving on, this is the sign test. I broke this one up into 2 separate tests. As per the user guide, it would be at 3 inches per second along the thrust axis, and then 7 Gs as well along the thrust axis. So starting with velocity, it's from 10 to 144 hertz. Some areas again that we've noticed, and same as the random test, that the cam roller and the L bracket stresses at 10 hertz. It's not that much, as you can see, so we're perfectly fine on that. Moving on, this is at 144 hertz. Once again, the L bracket was another area that showed a lot to us in this analysis at 5 PSI, but that's really nothing compared to the 40,000, almost 40,000 PSI of yield stress for 6061. Moving on, this is the acceleration where it'll be experiencing from 144 to 2000 at 7 Gs along the thrust axis. So here I have Overwatch at 2000 hertz. An area of concern was in between, if you can see that little orange dot of Overwatch by the cam. That I looked at the numbers, it was 6 PSI, 3 sigmas, 19 PSI. It won't be a major concern, but it's good to know what's going on with Overwatch. And what we took from this, to be honest, was to have more structural support. We have the weight for it, so it's something that we could most likely do.
Oh, okay. So for the electrical subsystem, we conducted a SPICE simulation focusing on the system startup and the motor deployment. For the system startup, we simulated 2 cases. The case A was in ideal conditions, and in a worst case scenario, we would see a current spike. For case B, we simulated the real world resistance from the 20-foot umbilical cable, and we were hoping that would dampen the surge to 27 amps. And for the motor deployment, we stress tested the stepper motor at 1 amp, and we wanted to measure the voltage ripple. The second thing is we simulated the millisecond zero startup to measure current surges. So for the system startup, in case A, we simulated minimal resistance at around 0.05 ohms. And we saw from the simulations, you can see the little spike on the left side. The capacitors acted like a short circuit, and it pulled a 65 current spike. And obviously that would pose a risk for fuse fatigue or instant failure on the launch pad. Therefore, we decided to use a ceramic fuse.
Yeah, so of course we also tested it with more realistic resistances from the umbilical cable and also from the fuse. Under these conditions, the current surge was much more manageable, only 27 amps for a fraction of a millisecond, so it's a pretty good result. The only thing we were left to change, like we said, was the fuse, so it could survive better and also help us with our temperature issues that we might encounter. Yeah, that's about it for that. And we also tested our stepper motor to see if there were any voltage ripples or any issues with the voltage ripples. The only change was very small. It wasn't really significant and it shouldn't be a problem.
Moving on to the software simulation, getting into the more details, we created a full mission simulation using environments like CMake and C++ systems. Going over it again, C++ is the fastest language, so we're going to work with that to validate flight logic before we actually deploy it into hardware. Working with our team, we simulated the entire mission cycle from liftoff to flight. This is a pseudo analysis, so it's going to be pretty similar to the event, but not fully same. We automated generation for telemetry event logs, so we're getting outputs that is the CVS for telemetry, the event log, and the mission summary that will be post after getting the first two documents done by an AI analysis. The vision for this is to have a suitable MVP before we actually deploy into our beta stages, so that we have a foolproof idea that our code actually works and before putting it into the Arduino boards. You can see the picture, we have a small analysis in CMake, you can see all these logs, and you can see in the end there's like the telemetry and text data that are being dumped onto the system itself.
This is the Overwatch PCB schematic. As you can see, there's minimal updates, and that's the footprint for the PCB board, and then the 3D model for the PCB board.
Yeah, the only thing worth noting about the 3D model is the Arduino will actually be on the back of it. So it's not there, as you can see.
As for the final phase of testing for Overwatch, we will conduct deployment system testing, worm gear system test, stress test, spring-loaded deployment test, locking cam node stress test, PCB part integration test, software startup test, and all of this will start to integrate with Scout once both subsystems are integrated with each other's systems in terms of RF connectivity. Can both systems do a software startup, and of course the deployment in general.
All right, now we move on to the Scout subsystem here. The overall power being used by Scout is 1,588 milliwatts. The data is not determined yet, but we've seen that it's not going to be an issue for transmitting data. The overall volume is 26 inches cubed, and the weight of the Scout alone with the electronics inside there should only be 3.6 pounds. This will be connected mechanically to Overwatch using a multi-point CAN system. The electrical connection will be made using magnetic pogo pins that stick on the back. The design is mostly final, no major changes to the dimension. The only thing we'll be updating is the updating mount solutions for the Langer probe, the antenna, and the pogo pins, and then just some minor changes for better machining. For a quick status update, we're about 30% complete tested. The only thing we haven't done to this that we did to the Overwatch was the FAA analysis, but we completed our 3D printed models. We have some here, and that's some pictures of the older ones. That was done about a week or two weeks ago, I believe. For the electronics update that are in, we already have the rock block in our hands. We got them this week, along with the XV radio modules. We also got our 5 and 3.3 volt regulators. Our IMUs are in, and our Arduinos are in. For the mechanical parts that are in, we got our electronics box that stays on Overwatch, and then all the gears and shafts are in too. The only items that are needed currently are the PCBs for Overwatch to be ordered, and then things that are like sealant and insulation for all the electronics.
For the Langer probe, what we are going to test is the vacuum testing. The materials that we're going with is high temperature ultra dense tungsten rods, non-porous ceramic aluminum tube for the insulation, machined aluminum 6061 housing, and PEEK TV used as an insulator. To test the electronics, we're going to use Arduino, custom PCB board, reliably provide voltage sweep across line of probe, and for the software, all electronics reliably send and store data in a recoverable manner. Final phase of testing for Scout. Our dates are deployment testing, February 16th, thermal testing, drop test, spring-loaded deployment test, heat shield testing, RF connection test, line of probe testing, subsystem testing and integration with Overwatch. After manufacturing both Overwatch and Scout, we will integrate both systems and start the deployment testing. The ISTR plan. So this is a step towards the ISTR. For the mechanical aspect, we need to complete full payload assembly and flight configurations, conduct vibrations testing, verify the center of gravity and mass properties, ensure structural integrity of deployables and probe. For the electrical, we have to integrate PCB, power, and inhibited circuitry, perform end-to-end power-up testing and flight configuration, ensure electrical isolation in all the modules, and finally, for software, we have to finalize flight firmware, validate sensor acquisition and data logging, simulate full mission timeline, and ensure that all faults are handled. Further on, our technical hurdles we are expecting is structural integrity during launch vibration, maintaining isolation and proper spacing during launch, ensuring Scout mounting is secure and releases reliably without interfering with the other team. On the electrical side, we high voltage stability and electrical isolation for the probe, and ensuring that the electrical noise is minimized to not muddle our data. For software, we just have to ensure that data is reliably logged, synchronization of measurements, and ensuring robust fault detection and recovery. Step towards the full mission simulation. Once again, just end-to-end mission timeline testing will establish mission readiness. Integrated hardware testing will establish that arrow is stable and reliable. By completing the full systems integration and environmental testing prior to the ISTR, we will be on schedule to do the full mission simulation by mid-April.
As for a summary test plan, for Overwatch final testing, we're doing the deployment system test, worm gear system stress test, spring-loaded deployment test, locking cam node stress test, PCB parts integration test, and software startup. As for Scout, same thing, deployment system testing, thermal testing, drop testing, spring-loaded deployment testing, heat shield testing, RF connection test, and a lanyard probe test. As for our Wallops testing plan, we NJIT RockSat team understands that following May 2026 testing, the experiment arrow will remain fully integrated in the Carroll structure for June 2026 flight. We acknowledge that there will be very limited access to experiment once integration is complete. For the testing overview at Wallops, we understand that we will have Wallops perform a vibration test in 3 axes, including sine and random vibration test. And we also understand that we are going to have a day in a life test where it's a full mission simulation, including power transmission, verification, time, event sequence, deployments, and data storage check. As for the test that we will like to have at Wallops or perform at Wallops would be the electrical system startup test, RF transmission test, make sure that both Overwatch and Scout actually have a stable connection. Our lanyard probe operates in full capacity. Our Scout deployment system actually works cohesively without any issues. Our software system works cohesively without any issues. And of course, yeah, that's about it for that. For the electrical startup system test, we want to do a cold start to verify the PUD powers correctly all critical components using GST2 line. Success criteria would be that all rails receive proper voltage within the 28 to plus or minus 4 voltage in nominal range. As for the RF transmission test, we want to verify the link between both Overwatch and Scout using the GST2 line and or battery powered. The success criteria would be both Overwatch and Scout have a successful, stable connection without interfering with Wallops communication. Yeah, the system data dump. Oh, sorry. For the system data dump, we want to simulate full flight duration and verify that the internal storage can handle and write transmitted data. We will verify that by removing the SD card and checking to see if any information was transmitted. As for the Lanyard probe operations test, we want to verify the Lanyard probe receives appropriate voltage to perform voltage sweeps. If the Lanyard probe receives a 50 volts and performs a voltage sweep, that is a successful criteria for us. As for deployment, we want to verify if we can perform 3 or more full cycle deployments to establish the motor towed baseline and expected launch sequence triggered by the time event 2. And system inhibits, we included the worm gear that provides mechanical inhibits that does not allow a back drive for our scout deployment. As for the day in the life while simulation, we want to include the following multiple full mission cycles, the both GSC and TE line compliance. All deployments must be triggered by the TE lines. The deployment speed must be met by requirement. The power constraints, arrow must not exceed the current drawings of limit of 1 amp hour mission battery. Structural integrity, make sure both Overwatch and Scout can withstand the anticipated Gs. And we are within the 15 pounds of verification and within 1 center mass of our deck plate. And of course, the software must work and execute a full mission simulation without innovation or failure. Our limited resources are batteries, gears, rods, and wear and tear on the cam lobes and a cam team.
All right, as we move on to the project management, this really didn't change. We still have our same advisors, Dr. Hillman Kim, Sodi as an advisor, and Gareth Perry. He is working with the New Jersey Space Grant Consortium, I believe. And then we have our project managers, me and Carlos, and then everyone else here. That not much has changed there. For project management, this is a pretty much full list of all the people working on the project. This did not really change from the last meeting. And then as for the timeline for the ISTR, we plan to do complete trip details, book hotels and vans and food that will be required for the trip by next week, as per required by the school. We want to do electronics testing and report starting next week, hopefully get it done by the end of the month. We want to make sure that all of our parts, our PCB and hardware, tooling, etc., is ordered by the end of the month. And then we want to start integration testing once all those parts start coming in. And then we'll start the ISTR presentation in a relatively healthy time before it's due. This is the updated milestone and event a sheet that you guys provided. I just want to put it in here so we're aware that it did change, especially these dates here. As for the budget, this is the total budget for the whole project. This has not changed from last time. And then for the student and mentor work plan for the STR, Yeoman helped us out, helped some of the full payload prototype. We also we didn't conduct any bench or test yet because none of the parts came in time. We did begin vibration testing, but only through FEA analysis. And then we'll just skip to the ISTR. For the ISTR, we plan to do final flight ready payload configuration, conduct integration, system and functional testing, and flight configuration, complete vibration, environmental, and thermal testing on a physical model rather than just on FEA. And then for the mentor, he's going to be attend and review all these tests and ensure that we're doing it correctly. He's going to verify that all the STR action items are closed and all the requirements are met. And then as for the estimated team size, we saw that only 4 people were allowed on site at a time, but we still plan on bringing 6 students and 1 faculty member. We understand that only 4 people will be allowed. And then this is just a budget breakdown for the whole trip. We budgeted pretty healthy for this trip anyways.
For conclusions, our biggest concern is Scout's electrical failure due to heat during reentry and a loss of data. Scout deployment failure, the gears may skip and or a spring failure, as well as the weight budget. As parts come in, we will anticipate overweight just for now, but we don't expect to be overweight regardless. Another big concern will be the Lanyard probe construction and of course the FUR document that we have to complete. As for plans to mitigate these concerns, we were going to excessively deploy start deployment testing on both the springs and the gear system, incorporate a heat shield or ceramic coating for Scout to mitigate any heat failure to internal electronic parts. And once all our parts are received, and more accurate weight of arrow will be provided. For our physics students, we're actually working together with them to build a Lanyard probe, and we're definitely consulting with Dr. Gilman about the Lanyard probe. For next steps, the finalization of Overwatch and Scout CAD drawings, the start of electrical and software integration and testing, deployment stress testing and spring gear system, finalize our PCB board testing, soldering electrical components onto the PCB boards, the construction of the Lanyard probe and testing, and of course, manufacturing of Arrow. So yeah, we do have a couple of questions.
Yeah, so starting with the first question, this was a thing that we realized in the user guide while designing, that all springs have to have, or anything with internal energy must have a velocity of 1 inch per second. We wanted to know, because it said with prior approval, we can go higher. So our question is to you, Wesley, if we can go higher than 1 inch per second. With the calculations that we've done with the spring that we have, we got 14 inches per second. So we wanted to know if that's permissible, or should we look into more other springs or designs?
All
Yeah,
right,
for
and then the other question. Oh, sorry. The only
Oh,
question-
sorry.
yeah.
Go ahead. We'll go after. We'll answer at the end. Sorry.
Yeah, I was gonna say the only other question that we had for you was the FUR document, but you can answer the spring question first.
Okay, my turn now. No, great work. Yeah, we'll just go over the questions. So as far as the spring, it's not super high of an ejection rate. We have had teams go that high. Generally, it's around 10 inches per second is what we see. 14, we'll have to run it past wall up safety, but I'm not immediately turned away from the idea. Let's just say that. But as far as chances, it's pretty high chances you'd be able to get that approved, but we will work through the process of getting that approved, considering this is an initial rate request. So I have made that note, and I will get back to you on the final yay or nay, but you can proceed in a couple different ways. You can proceed with the 14 inches per second that you expect, or if you can find something that's closer to 10, that would be a more guaranteed approval. That would also be a permissible route to go. But like I said, I'm not super worried about that rate. It's higher than we generally do, but it's not outlandish like 30.
Okay.
Alrighty.
And as FUR documents, we were having issues filling out the document itself. We had a few questions regarding the actual document, and maybe you could provide us some guidance.
Sure. Yeah.
Can you pull up the?
Yeah, we were wondering exactly. Let me see if I can find my mouse here. I believe I had it here somewhere. All right, sorry, I didn't have it pulled up, but let's see.
No worries.
In the meantime, do you have any questions for us?
Yeah, no, we can definitely, while you're pulling it up, I'll just go through what I have. But overall, great work, everyone. That's a lot of FEA testing. Not a lot of hardware testing at this point, but totally get the supply constraint as far as timing goes. It is a particularly rough year when it comes to sourcing materials, and that's pretty universal through all the teams. It does put you a little bit behind as far as an STR spec goes, but I think you can make it up for the ISTR as well and get all the testing done, as well as all the integrated testing done. I believe in you. Okay, yeah, first question though. Actually, just a couple notes. I did make the note that your TE is unchanged from Rev C, so that's all good. And I already have noted that you are running high voltage, so that is not a problem. I actually just thought of a second question on related to this. Let me write this quick note while I talk. So do we have Scout's final estimated ejection mass?
It should be within less than 5 pounds. I think we have it at 3.5 pounds. We're still waiting on a few updated 2.5.
It was 2.5 last time I checked. Yeah.
Wait, it says it right here. Yes, 3.6 pounds is what we.
Yeah.
And that's including all the electronics that we think are going to be on there and all the hardware.
Okay. So 14. Okay, so you're looking for about 10 to 14 inches per second at 3.6 pounds. This will go into energy calculations for safety. Okay. Alrighty. Back to the high voltage. There was another review I'm spacing on the institute. I'll have to look through my notes, but they were wondering how to build a vacuum plasma chamber, and it very much seems like you have done this right here. Is that a custom setup? Well, one, does it actually test anything to do with plasma? I'm assuming it does, but two, is it a custom setup?
Yes, this is a custom setup. It was actually made by a student last year, and it's been integrated into the physics major's capstones project essentially. So these are one of the labs that they actually conduct for their senior thesis. So it's all custom. We do have like a lab report on how to construct it, but it's very still work in progress.
Yeah, everything that's there was mostly ordered off of Amazon, if I'm not wrong. So it's pretty easy to make.
Yeah.
It's nothing like specialty that needs to be made.
Like there's JB Weld and tungsten wire and just tape everywhere, but generally it does what it needs to do to definitely test plasma for lanyard probes.
Sweet. Yeah, no, that's awesome. There was just another school that had mentioned it. They wanted to test plasma with portion of their experiment, and this popped up. But yeah, no, if you don't mind, I will point them in your direction with any questions. Feel free to help or point them in the right direction if you want. But yeah, nothing lost, nothing gained. But thank you. Next thing was on slide 22. Just Nebraska's power budget isn't part of your power requirements. So you can nix that. They have their own power margin. Their mass is pretty much the only thing I'm going to be tracking between the two of you. But with their experiment, you can basically go to your mass limit of that 15 pounds, and I'm not concerned with Nebraska's weight in addition to yours. Really, the one thing I'm tracking with this integration is just where their bolt holes are going to need to line up for their standoffs to get to that shelf that you designed. That's really the only thing I'm going to be looking at as far as that goes. So don't worry about keeping track of anything with their project. I think the only thing that we're going to need to keep track of is just the CAD models lining up, which I do have an updated CAD model from them that we will discuss here momentarily.
Yeah.
Alrighty. Next thing is, are you planning to charge at Wallops Flight Facility?
So I believe we're not charging our wallops at all. Everything's gonna be pretty much charged or pretty much.
The batteries we picked. Are you going? The batteries we picked, they don't have a very large self-discharge rate, and we plan on mechanically isolating the connectors, and hopefully when it releases, it can close that circuit loop. So we don't feel that that's going to be a big issue over the span of the month that's going to stay on the rocket.
Awesome, great to hear. Yeah, no, definitely testing will tell you all if you do need to or not. Just one thing to keep in mind, charging time is kind of an unknown depending on what we run into during integration and testing week, or even RBF procedures coming back in June. But yeah, you'll know more about your experiment as you test on further, and hopefully you find out that you absolutely don't need to charge and you're comfortable leaving it fully integrated and ready to go for launch from May. Awesome. Alrighty. All right, and then the one thing that caught my eye, and I'm glad I caught the time for this too, 65 amps at 28 volts. I am impressed. Noted that that's only 200 microseconds, so my concern immediately fell. Very low risk, but I do understand the risk analysis you are doing here as far as trying to mitigate any fuse wear, any trips. This is very, very not likely to trip the polyfuses on the vehicle. If the umbilical that you're using to test is a little bit different than the harness that we're using, which it will be. But the one thing I wanted to mention, if you wanted to, this is not a suggestion saying you have to, but one thing to consider that you may have already considered is just limiting it with just an inrush current limiter, like a NTC thermistor or something. But again, it's so short. 200 microseconds would probably, the only thing that'd catch that would be an E-fuse. So the EGSE will see that. It's not going to trip for you, though. I have those set a little higher than that. But yeah, no, that's an impressive amount of current for an impressively equal short amount of time. Just thought I'd point that out, but if you wanted to try to mitigate it, just some inrush current limiting protection will ensure that you don't blow any of your fuses or wallops. Well, you're not going to blow any wallops fuses, but now I'm just talking too much. All right.
Thank you.
But yeah, overall, everyone, great work. I love all the analysis that you're doing beforehand. The hardware testing will come. I know this is a lot of waiting for parts to come in, but the design work and the testing, the simulated testing is just as important. So I totally understand where y'all are coming from, and I'm excited to see where you are when it comes to ISTR time as well.
Hello. Sorry, I have a quick question.
Sure.
So you said, so yeah, we agreed that the 65 amp spike or the more realistic 27 amp spike will not trip the fuse. But we are trying to move away from the polyfuse because we found out it's a little like temperature dependent on its operation. Obviously, when it's going to be up in like the stratosphere, it's going to be really cold. Is there a more standard fuse that you guys recommend to use that we should look into? Because right now we're looking into like a slow blow ceramic fuse.
Yeah, so it's kind of a two-way approach. One's protecting against the actual inrush, and then the other approach is
Mhm.
trying to limit the inrush. But with the fuse, yeah, the polyfuses aren't great for catching these. They typically don't.
Yes.
The polyfuses I was referring to are actually on the vehicle themselves.
Mhm.
So they absolutely won't trip during this, so you're not going to make the rocket trip. But if you're trying to minimize the impact it's going to have on your experiment, maybe due to some electromechanical, wow, interference, long day.
Mhm.
Anyway, you would try to minimize it, which is why I brought up something like a NTC thermistor or just something that can help you avoid the spike in the first place.
Okay.
But I do agree it's extremely low risk.
Yeah.
I
Yeah.
assume that's more or less when you're powering up your motor drivers or something. It's pretty common, but the only thing that's going to see it
Yes. Okay.
is the EGSC during check-in.
All right. Okay. Perfect. Thank you.
Absolutely. Alrighty. Well, that is the end of my questions. I don't want to gloss over your fur form questions.
Do you have the document?
Oh yeah, I have the document here. I can see if I can just put it in the screen. Does it come over? No, it does not show. Nice. Okay. Oh, it does. Okay. We just kind of wanted some guidance on how to fill this out exactly, and like if we have to fill out everything, or what is the extent of all the information we have to fill out.
Yeah, so definitely. So starting with your frequency, you're going to aim for the band of frequencies you're going to be using. So in this case, for Wi-Fi, you'd be looking at the channel you're going to be using, assuming you're locking into, so say channel 1, you'd be on the lower side of that 2400 megahertz. But yeah, just find out what those frequencies are, list them. This is really for Wallops to be aware of and nothing related to necessarily interference, since Wi-Fi is such a robust protocol in the first place. The next thing, it looks like your organization and your project are all great. There's a bandwidth. Okay, yeah, number 7 is your bandwidth, which looks reasonable. If you're using something wider, like I don't know, like a 40 megahertz on a different, or for a different protocol entirely, like LoRa, can operate up here, but that looks fine. And then your contact information, yeah, this looks pretty standard. I'm not seeing anything that's standing out. You'll want to update your apogee, but that's really minor. I doubt Wallops would even flag that, but yeah. And then your transmitter information is everything that is going to be listed publicly. So if it has the FCC tag on it, this is where you'd be including it. But it looks like you filled it in completely, as far as what I'm seeing here. But yeah, the big ones are just the frequencies you're using, so we're aware of it. With Wi-Fi, it's less of an issue, but with LoRa and 6 teams that are using it this year, we are juggling as far as what channels everyone is allowed to use.
Okay, and then another question. Since we're using 2 systems, we're using the XV Pro and then the Rock Block. Do we have to fill out 2 of them, or can we combine the 2 into one form?
No, so 2 separate systems will be 2 different fur forms. Assuming they're, well, hold on. So the XB you're using, yeah. So they're 2 different systems. So you'll want to do 2 different fur forms for that for sure.
Okay, for sure. Thank you.
Yeah, great questions. But yeah, this is great work on this. I think this is not going to raise any eyebrows as far as that goes.
All right. Does anyone else have questions, comments, concerns?
No.
Leslie, do you have any questions for us? Any more questions?
Yeah, what I saw, it looks like you were in a really great spot to start testing with hardware in the loop here, which it sounds like is going to be happening soon. And then that will set you up for getting into ISTR and being successful there, minding that that is a month away, so don't feel like you have too much time there. This is kind of where teams get caught up if they're a little bit behind. You are a little bit behind, but you're not unrecoverably behind the curve. It's just going to be a little bit more stressful getting to ISTR, but teams have come back from a lot further behind. So I am not, I have faith in you. I do not think you will not be able to recover to ISTR. Again, more words. That's how you can tell it's been a long day. But as far as where you're at, I got all my questions. I love where you're at for the STR and how you're setting yourself up for success in the ISTR. And then the only really thing, there's going to be a couple action items, like I'd mentioned, related to your address for the deck or the deck, and then I will be setting up an email chain between you and Nebraska Lincoln, so we can get CAD models exchanged. And I'd love to see mainly where the holes that they need to have drilled in your experiment deck need to line up, and if their standoffs are going to fit. But everything else from their experiment should be essentially invisible to you, so they're not even going to use the same power connector as you. They're their own experiment. They have their own weight allotment, and then you can use as much of that 15 pounds as you would like.
Okay, that's good to know. Sorry.
Awesome. Awesome. Well, yeah, if y'all think of anything or run into any questions with the fur forms or anything else, feel free to reach out via email. Chris and I monitor that email equally, and then we will be in touch. And like I said, I will send those action items to you after this, and then we'll get cooking with New Jersey. Or not New Jersey, Nebraska. We'll get cooking New Jersey and Nebraska.
We'll update you on the whole payment process as soon as we hear back from our administrators.
Yeah, that's like pretty much set and done. It's just wait until Wednesday for the billing date to go out.
Copy that.
Right.
Sounds good. Well, everyone have a lovely weekend. Hopefully you're not getting too much snow over there.
Hopefully.
All right. Have a good one.
All right,
Have a good one.
Good weekend, guys.